Hi, everyone. Thanks for tuning into my presentation. I'm sorry to not be in Australia, but maybe we'll see you next time. This presentation is about long-term ensemble data-assimilated shoreline change modeling. I'm Vitousek. I work at the U.S. Geological Survey in Santa Cruz. And this talk is about some of the work that we've done to try to come up with predictions of shoreline change in different locations across the U.S. and across the world. I'd like to acknowledge my collaborators, which you see down here. This is an example of some of the shoreline change modeling that we've done with Cosmos Coast model. Here you see Southern California, and at this location, which is very close to Scripps Pier in La Jolla, you see a time series of wave heights and a time series of shoreline change predictions. And as you can see at this beach, the shoreline responds very closely to the wave conditions. Whenever you have large waves in the wintertime, you have erosion, and when you have smaller waves in the summertime, you have accretion. We have some measurements, which you see at these blue dots along this transect. And this model assimilates that data to try to tune its model parameters and come up with the best prediction of shoreline change at this given location. And because the model is assimilating all this data, it does a pretty good job of capturing the actual observations of shoreline change at this location. And now what we want to do is we want to figure out how to make projections. Now that we've calibrated this model, can we predict what the shoreline is going to look like? Well, of course, because shoreline position is very much driven by the wave heights, forecasts of shoreline change rely heavily on good forecasts of wave conditions. So we set out to ask the question and to understand what are the differences between shoreline change predictions and their uncertainty estimates with and without ensemble wave conditions. This example is without ensemble wave condition. It just uses a single time series of wave conditions to provide a projection of shoreline change. But in the future, we don't know what the wave conditions are in any deterministic sense. In a statistical sense, we understand this behavior of large waves in the winter and smaller waves in the summer at this location in particular. But going forward, it would be much better to make a projection of shoreline change using ensemble wave conditions because we don't know what the waves are going to be like in the future. Seems like a natural thing to do to understand the differences between shoreline change predictions and uncertainty estimates, both with and without ensemble wave conditions. So to do this, we're using a model that we developed called Cosmos Coast. This model simulates the evolution of the shoreline Y as a combination of different processes. Some of them are long-term, like longshore transport, shoreline recession due to sea level rise, and other long-term residual effects like fluvial inputs or sediment supply. And there are other short-term processes like the cross-shore shoreline response due to waves, which we'll talk a lot about from here on out. So for this work, we're going to ignore the long-term processes and just focus on understanding the behavior of shoreline change predictions on this short-term process here. And the reason that we're focusing on this process is because most shoreline change observations and predictions where we're located in California, most of the variance in the observations is really determined by this, which is being determined by how the waves influence the shoreline position. And the model that we use in Cosmos Coast to do this is a popular Yates et al. Equilibrium shoreline model from 2009. And this is what that model looks like. This and this term are basically the same in the context of Cosmos Coast. But I'll get into this a little bit more. This model from Yates et al. 2009 was reformulated by Blasier et al. 2017. And the two blue equations here are exactly the same. It's just a reformulation, provided that YEQ, which is called the equilibrium shoreline position, is equal to E minus B divided by A. And here E is just the wave energy, B is just a background wave energy parameter, A is another sort of wave energy with relation to the shoreline position parameter. And here the equilibrium timescale tau is just 1 over CA e to the 1/2, and C is another parameter in the Yates model. So the main parameters in this model are C, A, and B. Here we've reformulated that model a little bit more. And the reason that we've done so is because we want to improve our physical intuition about the parameters C, A, and B. So we've done this by just doing some pretty simple math. You just multiply by B over B and swap the B with the A. And then you can regroup this parameter, which is a negative B divided by A. We call that delta Y. And that delta Y just represents a shoreline excursion or shoreline erosion length scale. And so this YEQ term is just minus this delta Y parameter times the wave energy anomaly here. And then the time scale is just reformulated by, you can multiply by B to the 1/2 over B to the 1/2 and rearrange the denominator. And you can create a new parameter here, which is delta T, big T, and that is just a timescale parameter, a background constant timescale parameter. And you can see that this other term here, which is the ratio of the wave height to the background wave height, which is HS bar, makes it so that the equilibrium timescale becomes shorter when the waves are larger, and it becomes longer when the waves are smaller. So this is a summary of the changes between the Yates 2009 model and the current model. The original parameters were C, A, and B, and those parameters didn't necessarily have the most intuitive dimensions based on this formulation. B has a straightforward dimension of wave energy, but A is a little bit more confusing and C is a little bit more confusing. Also here, A is a parameter that needs to be negative, and C is also a parameter that needs to be negative. And by doing this formulation, the new parameters are just delta T, delta Y, and HS bar. All those parameters are positive, and they have straightforward dimensions of time or length. So for this example, which I'll show next at Tairua Beach, New Zealand, the parameters, the best fit parameters of our shoreline change simulation are about a month for delta T, about 10 meters for delta Y, and HS bar is about 1.2 meters, which is very close to the average value of the wave height. So here I'm now showing some simulations of that modified Yates model for 3 different periods at Tairua Beach, New Zealand, which was a well-modeled beach as part of this shore shop workshop in New Zealand. So I split this simulation up into 3 different periods. The first is a hindcast calibration period when data assimilation is taking place. The next period is a forecast validation period where there's no data assimilation taking place, and the fit between the shoreline position and the observations, which are in the blue dots, give a good indication of the performance of the model. And finally, a projection period where we have no more data and we're trying to make a prediction of what the shoreline is going to be in the future. And here you can see a time series of the wave heights. And here in the projection period, we're only using a uniform or deterministic wave forcing. We're only using one time series of wave conditions to force this model. And here the variance is created because we're adding some noise to the simulation and we're running it with a range of different parameters. So this next example is where we use an ensemble of wave forcing conditions, and those ensemble is produced by a wave model from Kagagal et al. 2020. And so you see here, when we're making a true projection, we don't necessarily know what the wave conditions are. So in this case, we're running the model with 1,000 different time series of potential wave conditions and seeing what the shoreline position is in the ensemble mean and the uncertainty bands in green, yellow, and red here. And so you can see it's a very different look to the model as opposed to the previous example of the uniform forcing. One thing that we noticed here was that the widths of these confidence intervals in blue are relatively constant with time. And you can see this even better when you look at the standard deviation or the square root of the variance of that ensemble over time for these different periods. Here you can see that the variance of the model in blue of the uniform wave forcing, it oscillates back and forth, but it has a relatively constant background value. And the same thing with the ensemble wave forcing simulation in red, has a higher value of the uncertainty during the projection period, as is the case because we're running it with a time series of ensemble wave conditions. Has a higher value of the uncertainty, about 60% more uncertainty, or if you square those values, it's about 150% more variance. And what we'll show next is that we can actually predict approximately the background value of uncertainty using some analytical. To derive the constant background values of both the uniform simulation and the ensemble simulation, we create an idealized model that's the combination of damping, forcing, and noise. And using that, we can show that the variance of the ensemble is created by the relationship between the amount of damping and how much noise is being added. In the case of the ensemble force simulation, it's how much noise is being added to the simulation and also the inherent or intrinsic noise associated with the wave forcing. The two factors combine to give you the overall uncertainty. All of the details are discussed in a paper that we have under review at JGR Earth Surface, and if you want to know the details, you can please reach out. But the summary is, with some analytical work, uncertainty can be quantified in a straightforward manner. Thanks very much for tuning into my presentation. I hope this was interesting, and stay safe out there. Bye.